Okay, can everyone see this on the screen?
Yes, sir.
Yeah, fine. So this is the block diagram representation, and then we represent the step response. I have said yesterday what is meant by step response. So specifically unit step response like this: C of s equal to G of s into R of s, where R of s is the Laplace transform of the step function, unit step function. Fine. So this will be equal to A divided by s plus A into the Laplace transform of R of s, which is equal to 1 by s. So these things are very simple mathematics. There is nothing much calculation or algebra required. So substitute what is g of s, then multiply it with the Laplace transform of unit step function. Okay. So then I want to get the inverse Laplace transform to plot the graph with respect to time. You cannot plot the graph with respect to s because s is a complex frequency. Okay. So s is a complex frequency. We talk about what is this complex frequency mean in the probably in fourth or fifth unit. So till then, you assume S as a Laplace transform function, which is also called as complex frequency element. Fine. So to get or to plot the response in time domain, we want to have the expression in time domain. So C of S, which is the Laplace transform of output, can be converted into time domain only when you apply inverse Laplace transform. Okay, a mathematical tool called inverse Laplace transform, and to apply that we have to take the partial fraction of this element and again represent the parameters in a standard form, that is 1 divided by s minus 1 divided by s plus a. So I'm not going to write how the partial fraction is taken for the simplest expression. Okay, there are some more complex expressions in the upcoming chapters, then I will explain. But for this particular expression, everyone have to try out yourself, and you can easily get the 1 by s minus 1 divided by s plus a expression after taking the partial fraction. So these are in standard form, and you can apply the inverse Laplace transform very easily. So what is C of s now? It is 1 divided by s minus 1 divided by s plus a. You can work out parallelly. Then we arrive at C of t equal to, what is the inverse Laplace of 1 by s? It is 1. And what is the inverse Laplace of 1 divided by s plus a? It is e raised to minus at. Okay. So this is through inverse Laplace transform. So is it clear for everyone? We started with the first order system where we had only one pole or one characteristic root of the system. Then we took the inverse Laplace of the output to get the expression for output of a first order system in time domain. This is very simple. So next, what is A? What is this A is called as? It is some positive constant. How and why we have to consider that all I will explain soon. So for time being, just understand the mathematics behind this. So when you plot C of t with respect to t, so C of t is output of a first order system. So I have said the response of a system means it is always output of a system. So what I will do is I will plot the behavior of the system, which is nothing but which is always expressed in terms of output of the system. So I will plot a graph on which x-axis is time. You can take it in a scale of seconds or milliseconds, whatever you want. So x-axis is essentially time and y-axis is the output magnitude or output C of t. So in the same graph, I represent the unit step input, which has a magnitude of 1 and it is called as R of t. So my input will always remain unity throughout the time. And for this input, what is the expected approximate output? So this is how you can expect your output. A gradually increasing output. And I term it as obviously C of t. So this is like very obvious. Okay. One can judge this for any positive constant A, you end up with this type of graph. Or what is the other way to explain this, how to get this graph is so some positive value of a. What you can do it in a simplest way is you can make two columns for t and c of t. So one column for t, another column for the value of c of t for a given value of t. Assuming a is some positive constant, you can assume it as 1, 1.5, 2, 2.5, anything. So then what you can do is you plot a diagram and give some values to this independent variable t and calculate the relevant value of output for that particular t and go on representing that in the graph. Then you will end up with this shape of the output. Fine. So any doubts till this point? So I just repeat once again. We started with a analysis of first order system. We considered the standard transfer function, which is g of s equal to a divided by s plus a. Then we solved for inverse Laplace for a given step input. Fine. And then we plotted the response on the graph with a time scale. So that's it for the first order system. So what all we can understand from this graph? So let us look further. Okay, so before understanding the graph, let me ask one question. What is the value of A or how the value of A can be defined? Okay, in the transfer function we had A divided by S plus A. So from where that A is coming? That is the question. Right? So A is obtained from the dynamics of the system or the system dynamics. Okay, so we already did this type of example in one of the introductory class. So for a mechanical system, in which the transfer function can be written as x of s divided by f of s equal to 1 divided by bs plus k. Ignoring the mass, if we write the transfer function as 1 divided by bs plus k, and if you assume k equal to 1 and b equal to 1, we get g of s equal to 1 divided by s plus 1. Okay, so what is the a value here? It is equal to 1. So this is in the standard form, a divided by s plus a. Therefore, you can term a equals to 1. So the constant, positive constant a comes from the dynamics of the system. So immediately one can have a doubt, why can't a be negative? Okay, why can't the constant a can be negative? So this particular example will answer that question. Can we have a negative value for a, or if a has a negative value, how you can interpret the actual dynamics of the system? So you question yourself and try to find the answer yourself. It's basically based on the physics. So having a equal to negative is as good as you are having a negative spring constant. So what is the meaning of negative spring constant? Is there any spring which has a negative spring constant? So you just dig upon that. I will proceed with other type of example. We have g of s equal to 2 divided by s plus 4. Is it in a standard form? No. We don't have it in a standard form because the numerator is 2. Numerator is 2. So one can question what is the value of a in such cases. So the thing is, convert this to a standard form as g of s equal to 1 divided by 2 into 4 divided by s plus 4. So now you can say equal to 4. Now you can say a equal to 4, and if you are taking the note, you still put a question mark for this. Is a is actually equal to 4? Can we still consider a is equal to 4? And try to find the answer for this. Fine. So when the transfer function is not in standard form, I have suggested a technique to convert this to a standard form and define a equal to 4. Okay. I'm not telling that I'm correct or wrong, but I will leave this question for a moment up to you. Can we consider the constant a equal to 4 after the conversion? So I'll answer this particular question while solving the numerical. Fine. So as of now, you remember what is meant by standard form. Fine. Then after this we proceed with the next part, finding the C of t for the second example. So you will end up with C of t equal to 1 by 2 into 1 minus e raised to minus 4t. Please cross verify my answers. Do not copy them blindly. If you're not getting time now, you can cross verify it later, and please let me know if there is any mistake. Fine. So this is the C of t for the second example. So you can observe that there is 1 by 2 present here. Is 1 by 2 present here. So will it make it a standard form? That is the question that everyone will keep in mind. So why I'm highlighting is that like you can get a gate numerical of this kind. So I'll leave the question in your mind and then we can solve later. So after this, we proceed with the time domain specification. Time domain specifications of first order system. So what is meant by time domain specification? So everyone knows the general meaning of specifications. Okay, specifications of a motor, specifications of a generator. Okay, they define what is specific about those motors, or they may define even the design aspects of that particular machine. So similar to that, we define some terminologies specific to first order system or specific to first order system behavior. So those terminologies are termed as time domain specifications. Since we are doing it on time scale, obviously it is time domain specifications. So when I say time domain specifications, it's by default means with respect to time only. So we study those specifications for the first order, and in the other class we move on to the second order. So what is the first specification? So the first specification is time constant. Time constant. So you might have heard the word time constant in RC circuit. In RC circuit. So let us see what it means in control system or control theory. So time constant, to define time constant, first let us consider the output expression of a standard first order. Then substitute t equal to 1 by a in this expression. So what we get is 1 minus e raised to minus a as it is, replace t by 1 by a. This is equal to 1 minus e raised to minus 1. So use your calculator to find e raised to minus 1 and you will get this equals to 0.63. So C of t is equal to, or the output is equal to 0.63 when t is equal to 1 by a. 1 by a. So let us locate this point on the graph. We have unity magnitude on y-axis at this point. 0.63 means it is obviously less than 1, and approximately I have marked it here. So to reach 0.63, it takes some time. It takes some time. And that time is equal to 1 by a on the time scale, 1 by a seconds. So at 1 by a seconds, if you make a table and calculate for 1 by a seconds, your output is 0.63. Okay. And that particular time is termed as time constant. It is a simple definition. Time constant is given by 1 by a for the first order system. So in simplest terminologies, therefore we can call time constant as it is the time taken by the step response. Taken by the step response or unit step response to be specific. Taken by the step response to reach or to rise 63% of its final value. Okay, I've just given another terminology here, final value. So what is that final value is after certain amount of time my response of the system is remaining constant. Is remaining constant. Why it is remaining constant? Because if you look at this expression, okay, as t goes on increasing, as t goes on increasing, this particular term is becoming zero. Okay, because it is negative power. So as t increases, this term becomes zero, and essentially we will have, ultimately c of t for a increased value of t equal to 1. So at particular time, it will obviously reach and settle at final value, and that final value is nothing but unity. And what is the initial value? Initial value is at t equal to 0. So at t equal to 0, e raised to 0 is 1, 1 minus 1 is 0. So c of 0 or the initial value is 0. That is obvious from the graph. So final value is 1, and with respect to final value, one can tell a generalized definition. This is a generalized definition. So it is the time taken by the step response to rise or to reach 63% of its final value. So why I'm telling this as a generalized definition is, if you look into some other practical aspects of scenario, the input applied is not always 1. The input applied is not always 1. It may be more than 1, or it may be even lesser than 1. Then we need to consider 63% of final value. Right? So in this particular example, 63% of the final value, which is unity, is 0.63. Straight away, it is 0.63. Any doubts and clarification in time constant?
Excuse me, sir.
Yes,
So this 63%, does it have any other physical significance, or are we just taking it as a standard for all systems?
it has a significance in the sense it is accepted, conventionally accepted everywhere. You can ask like why we cannot take t equal to 1 by 2a or 2 by a or 3 by a. There are many questions you can get, but whatever literature I have studied till now in control system, I felt it is a convention that everyone is accepted. So when I say time constant is say 5 seconds for one system and time constant is 10 for other seconds, you can make a difference, right? You have a RC circuit. One RC circuit is taking 5 seconds. One RC circuit has 5 seconds time constant. Another has a 10 seconds of time constant. So you can make out the difference, right? What
Yes, sir.
essentially means the time constant in RC circuit? How we refer the time constant for RC circuit? It is with respect to charging of capacitor, correct?
Yes, sir.
Yes. So there also we define it in the same way, but the interpretation may goes different. But
So, a
huh,
student is waiting for you, sir, to accept.
huh? Come
Someone is
again?
waiting for you to accept, sir. Your
Okay,
the
okay,
next
okay,
practice.
okay. Yes, fine. So it is universally accepted convention, I feel. Okay, the one who had asked the doubt. There's no meaning in considering it in other way. I
Okay,
mean,
sir.
mathematically and conceptually, it gives many ideas about the dynamics of the system. When I particularly give you the specification of a system, and if I mention time constant for this system is so and so, like you can make out many conclusions out of it about the dynamics. Conceptually, it goes like that, but mathematically, it is uh, accepted, universally accepted convention. Fine.
Okay,
So
sir.
be careful with respect to this definition. You should always deal it with respect to final value. Okay, 63% of its final value. So when the final value is other than 1, say if it is 10, if I have applied a step change function of magnitude 10, then my time constant definition is the time taken to reach 6.3 of the final value. So that's it. Next, moving to the next specification, the second specification, which is called as rise time, which is called as rise time. So how we define the rise time? It is the time taken by the step response to reach from 10% to 90% of its final value. Okay, so definition of rise time. So why it is 10 to 90 and all, we are not supposed to question. Okay, it is the convention made by researchers. Okay, so and the same culture has been continued, and it is again considered even in the design cases also. So for this particular example, 10% and 90% means zero point 0.1 and zero point 0.9 because our final value is 1. So 10% of final value is 0.1 and 90% of the final value is zero point 0.9. So I am marking on the time scale, on the graph, I'm marking the time scale for 0.1 and 0.9, and this particular time, okay, just hold on for a minute. Okay, can you see this now, Ganesh?
Yes, sir.
Okay. So this particular time from point 1 to point 9, I'll mark it as TR. Okay, from here to here, TR. That is rise time graphically. But is there any formula exist to define this mathematically? Okay, is there any formula for the rise time we can derive? Think. Very simple. Yes, there of course exists a formula which we can derive as follows. So we know the output C of t equal to 1 minus e raised to minus t. So how do I get TR from this? So let me make some definitions. So I will call the output at t1 time is as 0.1 and output at t2 time as 0.9. This 90%, this 10%, which occur at two different instants of time. I'm just making a definition. So find t1 from this by solving this first equation and find t2 from this by solving this equation again. So once you find t1 and t2, can I call the difference of t2 and t1 as rise time? Difference of t1 and t2 as rise time? Yes, you can. I'll call this as t1. I will call this as t2. I'm not writing it here because using sketch pen and writing so many terminologies will not make this graph to look good. So just assume this as t1, this as t2. So t2 minus t1 is tr. It's not so complex. So how to find t1 and t2 now? How to find t1 and t2? So substitute here c of t1, just c of t1 equal to 1 minus e raised to minus at1 equal to 0.1. So this is from first expression. Then from the second expression, it is 1 minus e raised to minus at2 equal to 0.9 and solve for t1 and t2. How to solve this for t1 and t2? Again, it's very simple steps. I'll give you a hint. You can try it for 1 minute. And if you're not getting, just wait. I have solved it in the next slide. Immediately after this. So solving is very simple. Take this term other side. Take 0.9 on this side. Then you have e raised to minus at2 here and 0.1 here. Then apply natural logarithm ln of 0.1. Then proceed for t1 and t2. The same step for this t1 also. So solving this, we get approximately t1 as 0.1 by a and t2 as 2.3 by a. Okay, t1 as 0.1 by a, t2 as 2.3 by a. Therefore, rise time is difference of that. So what will be the answer? 2.2 by a. Fine. So I'll repeat again. The rise time is the time taken by the step response to reach 10% to 90% of its final value. its final value. So this is how you can get it. Fine. So next we'll move on to the third specification. It is settling time. Settling time, and the symbol is T subscript S. T subscript S. It is defined as the time taken by the response to reach 98% of its final value. 98% of its final value. So we studied about 63%, we understood about 10% and 90%. Now it's 98% of its final value. So the settling time is the time taken to reach by the response to 98% of its final value. So for unit step input, 98% is obviously 0.98. So let me mark 0.98 in the graph. So it is very much nearer to the unity, there is no doubt. Very much nearer to the unity, so 0.98, and this particular time I will mark it as TS. Okay. Settling time TS. So again, can we find the formula for this TS? Okay, I will pause it for 3 to 4 minutes. 3 to 4 minutes, and everyone should try to find the formula for TS. So what we know, what data we know is 98% of the final value. So can everyone try to find this? I'll put the previous video for a reference, previous slide for the reference. So take this as a reference and find TS now instead of TN.
4 by
So, hello?
4 by A. So 3.91 by A.
3.91
by A.
Okay, anybody else who is trying? Take your time and find the answer.
3.91 by S.
Yes, I will ask some specific people. Okay, Meenakshi L, are you calculating?
Yes, sir. It's 3.91 by 8.
Okay, then Tejas K, are you calculating?
Yes, sir. I said 4 by A. I approximated.
Okay, you said. Then Prakriti, Puneet, are you able to calculate? Rahul, you can answer.
Doing, sir.
Doing, okay. Shashank, Shravani, Shweta, Siri, Shrikar. I hope you are doing.
Yes, sir. 3.91 by 8.
Okay,
Yes, sir.
3.91 by 8. Fine. Everyone should get this. It is 3.91 by 8. Let us see how you can get it 3.91 by A. Those who are not able to calculate, just have a look at this video. So we can define C of Ts equal to 1 minus e raised to minus ATS, then that is equal to 0.98. So rearranging this, you will get 1 minus 0.98 equal to e raised to minus ATS. Then as I said, you have to apply the natural algorithm ln of 0.02, which is minus 3.912. So Ts is equal to 3.912 divided by A, and it is approximated to 4. it is approximated to 4. So this is again the convention accepted by all the designers. So settling time, you can approximate it to 4 divided by 8. Fine. So these are very simple. So how to derive the expression, derive the formula should start from here. So if you know the concept clearly, you can put mathematics easily. So finally, we have three specifications for the first order system. First one is time constant. Second one is rise time. And the third one is settling time TS, which is equal to 4 divided by 4, 4 divided by A seconds. 4 divided by A seconds. So let us take one simplest example. So for the time domain specification, find the time domain specification for the system given by 5 divided by S plus 5. Very simple. So you have to find time constant, then rise time, then settling time. So rise time is, sorry, time constant is 1 divided by 5 seconds. So similarly, you can find for the other two. Fine. So this is very easy task. So this is about the first order system. Then in the next class, we study time domain analysis of second order system.